class, now it's time for us to talk about some of the unique properties of water that are very important for some of the weather processes that we're going to be spending a lot of time looking at this semester. So remember, water vapor is one of the most important gases in the atmosphere for weather processes, and one of the reasons for that is that water exhibits these really unique properties. And remember, the reason for that is that water has this interesting molecular structure that causes it to have a negative charge on one side and a positive charge on the other, which we call that being a polar molecule. And because of these different charges, the opposite charges attract each other, and those bonds are what we call hydrogen bonds. And these hydrogen bonds are pretty strong, and because they're pretty strong, water exhibits some unique properties. And one of those is that it exists in all three phases: solid, ice, liquid water, and water vapor, or the gaseous phase, all at normal Earth's surface temperatures. And that causes water to be very abundant at our Earth's surface. Also, ice floats. That environmentally is a very important characteristic of water, and that occurs because its density decreases when freezing, and we'll talk about why that is in just a minute. Another really interesting property of water that is very important to environmental processes and weather processes is that it takes a lot of energy to change the temperature of water. That's what we call the specific heat, the amount of energy necessary to change the temperature of a substance 1 degree. And this is very high for water. And so because of that, water can absorb a lot of heat energy without its temperature changing a whole lot. Remember, we talked about differential heating of land and water, and that's because of this high specific heat or heat capacity of water. It also requires a lot of energy to evaporate water, which is to change it from its liquid state to its gaseous state. And again, that's because we have to bust hydrogen bonds, right? So hydrogen bonds are the reason for that. And then it also takes a lot of energy to melt water from its solid or ice state into its liquid water state, because, again, we have to break hydrogen bonds. And water is also a great solvent because of its polar structure. It can actually form hydrogen bonds with other molecules, with other substances, and so it dissolves other substances really readily. Now, this list of unique properties is very important for us in this class, and in particular, these three here that have to do with energy distribution around the globe and regulating our Earth's climate. And remember, the underlying reason for these properties is that water can form hydrogen bonds. All right, so first, let's talk a little bit about the density of water. And the density of water varies with temperature. So here we have a graph of the density of water. And notice it's going from 0.9 to 1.02 grams per cubic centimeter. That's mass per unit volume. And then we have temperature on this axis in degrees Celsius. We go from -10 up to 50. And we can see that the density from -10 to 0 is about 0.92. And then we jump up to a density of 1, and then we decrease a little bit. So in its liquid form here, we can see that the density increases and then decreases. So where is the maximum density of water? At what temperature? Well, what we find is that is actually at about 4 degrees Celsius. So the maximum density is at 4 degrees Celsius. So that's in its liquid form. So if we cool it colder than 4 degrees, the density decreases. And so the density of solid water or ice is actually less than the density of liquid water. And as a result, ice floats. So does anything else cause the density of water to vary? Yes, it does. Seawater has a different density than fresh water. If we dissolve minerals, suspended solids, and they can also change our water density, increase it. We typically use a value of 1 gram per cubic centimeter for density at normal Earth surface temperatures. So let's talk a little bit about why it is now that the density decreases when we freeze water, when we change it from its liquid to its solid form. And this diagram sort of helps with that. So here is our solid ice form. These are our water molecules. Here's our liquid form, and here's our gaseous form. And just notice the distance between the molecules here. When we go from liquid form to solid form, what happens is those molecules move into a crystalline structure. So at temperatures below 0 degrees Celsius, these hydrogen bonds form a 3D crystal lattice of water molecules. And these are actually microscopic images of ice crystals. And you can see with the naked eye, you can see beautiful crystals that form. That's the reason that we have such beautiful ice crystals. And then if we warm water to about 0 degrees Celsius, we start breaking some of those hydrogen bonds. And that lattice starts to collapse. And when it collapses, the molecules move closer together, and so water becomes more dense. When it freezes, they move further apart. They form this solid lattice structure, and it takes up less space, so the density decreases. And then if it melts again, then they break down and they move closer together, and the density increases. So ice floats. Well, we can talk about what happens if ice doesn't float later, but just, do you think anything would melt? If a pond froze from the bottom up, we might have a pretty cold planet. It would be different. Okay, another phase change that's important is evaporation. And so this is moving from liquid water to the vapor form. And this takes a lot of energy because, again, this time we're completely breaking a lot of hydrogen bonds to bust these water molecules free so that they can move into the gaseous form. Evaporation can happen below 100 degrees Celsius. 100 degrees Celsius is the boiling point of water, which means the vapor pressure of the water vapor in liquid equals the water vapor pressure in the gaseous phase, and so that's why we see these bubbles moving up. That is what defines the boiling point. And that's when we start breaking all of those hydrogen bonds and releasing all of those water molecules into the gaseous form. So both melting and evaporation require a lot of energy. So let's go back to look at our phase changes. So we can go from solid form to liquid form, which we call melting, and that requires about 80 calories of energy per gram of water. Or we can go from liquid form to solid form, which releases about 80 calories of energy. And that amount of energy is what we call our latent heat of fusion. And then if we look at our evaporation phase change, going from liquid form to gaseous form, it requires 600 calories. So it takes a lot more energy to evaporate 1 gram of water than it does to melt one. And again, that's because we have to break all of those hydrogen bonds to set those water molecules free. And then when we condense or go from gas back to liquid, then we release about 600 calories of energy. We can skip the liquid form and go straight from solid to gas. In the state of Colorado, we lose a lot of our snow through this process called sublimation. You could think of it as sort of evaporating snow, but it skips the liquid phase. It goes straight from solid to gas. And notice when we sublimate, we absorb about 680 calories of energy. So we have 80 plus 600. So the combination of those two is the amount of energy needed to go from solid to gaseous form. And then deposition is the opposite of that. So these phase changes, melting and freezing, boiling, condensing, we know take place at the melting freezing point is 0 degrees Celsius and the boiling condensing point is 100 degrees Celsius. Now, what's really interesting about water is those temperatures are really anomalous. They're very strange. If we look at some other hydride molecules, these are group 6A hydrides, so sulfur hydride, selenium hydride. What we see is that, and this is increasing molecular weight, so basically the atomic mass of oxygen is less than that of sulfur, which is less than that of selenium. And so this is increasing molecular weight if we go to the right. And so if we start with other hydride molecules, you can see what their boiling points are and how the boiling point decreases as we decrease the molecular weight, and the freezing point decreases as we decrease the molecular weight. And now, if water did not form hydrogen bonds, if it was not such a strongly polar molecule, its freezing point would be down here at about minus 90 degrees Celsius, and it would boil at about minus 70 degrees Celsius. And so what would that mean for which phase would water be in on Earth if that was its boiling point? We would pretty much only have water in its gaseous phase, right? Because our normal Earth's surface temperatures are right up in here, in this range. And so that means we would only have water in its gaseous phase. But thankfully, because water can form hydrogen bonds, its melting freezing point is 0 degrees Celsius and its boiling condensing point is 100 degrees Celsius. And because of that, then we can have water existing in its solid phase, in its liquid phase, and in its gaseous phase, all at normal Earth surface temperatures. So, latent heat. So this is that energy that's necessary to change a given mass of a substance from one phase to another phase. And the key here is that the temperature doesn't change. So that energy is all expended in the phase change. And for the case of water, it's all expended in either breaking hydrogen bonds or it's released by forming hydrogen bonds. And so this is kind of a helpful little diagram. So as we go to the right here, where it's a change in time, we're moving forward in time, and we're adding heat at a uniform rate. So we start with ice at minus 20 degrees, and we start adding some heat. And so as we add that heat, the temperature of the ice increases, and we hit 0, and notice the temperature stays at 0, but we keep adding heat. We have to add 80 calories of heat, and we change it now to liquid water. So now we can have ice at 0, or we can have liquid water at 0. And so now we have liquid water at 0. We're going to keep adding some heat, and we're going to change the temperature from 0 to 20 to 40 to 60 to 80, and we hit 100 degrees Celsius. And now we're going to have to add about 600 calories in order to change that water to steam. And notice we have liquid water at 100 degrees Celsius, and we have steam at 100 degrees Celsius. So the temperature hasn't changed. All of that energy that we've added has gone into changing the phase from liquid to gas. So our latent heat of fusion is this 80 calories that's necessary to change water from its solid form to its liquid form, and the latent heat of vaporization, about 600 calories, is necessary to change water from liquid to gas. And no temperature change happens with those changes. All right, so just to summarize, here's our solid phase, here's our gaseous phase. We can take on 600 calories in the process of sublimation, or we can release 680 calories in the process of deposition. We can undergo melting, which takes 80 calories. We freeze, releases 80 calories. To evaporate, we absorb 600 calories. To condense, we release 600 calories. Those are some of the important properties of water that we need to think about for weather and climate related processes. And that is that hydrogen bonds result in water having a very high specific heat or heat capacity, which means it takes a lot of energy to change the temperature just a little bit. We have a very high latent heat of fusion, which is this amount of energy necessary for melting. Water has a very high latent heat of evaporation, which is the energy that's necessary to go from liquid to gas.